Good morning, children. This is the sixth video, children, of periodic classification, and in today's session we will be talking about electron gain enthalpy and what factors affect and how does it vary in the group and period. Let's define what is electron gain enthalpy. See, so far we have talked about two periodic properties, atomic radius and ionization enthalpy. Now we are talking about the third one, right? So let us define what is this. It is defined as the energy released. It is the energy released when electron is added to neutral isolated gaseous atom. Okay, when electron is added to the valence shell, you can add here to the valence shell of the neutral isolated gaseous atom. Each term is important. It has to be neutral, it has to be isolated, and one very important thing is, in this process the energy is released. It is always released. That means we can say it is exothermic. It is exothermic. Energy will be released. And how do we represent this? We represent like this. This is enthalpy. This is electron gain enthalpy. Delta means the energy change. H stands for enthalpy. Eg is electron gain. So electron gain enthalpy. This is a symbol for it. Let's take example, right? Suppose I have some atom X. This is of course in the gaseous state. If it takes electron, it will form X minus also in the gaseous state, and in this process energy is released, which we call as, if I write, this will be minus. This is the energy release, minus electron gain enthalpy. If I am writing the equation, I may write this as plus electron gain enthalpy, means it is released. In the product side it is given out, right? I can also write delta H is equal to minus electron gain enthalpy. Delta H is the enthalpy of the reaction. Okay, we will be also talking about these in thermodynamics chapter, right? So this is the first electron added. When the first electron is added, it is always added to the neutral gaseous atom, and it always results in the formation of uni-negative ion, right? So we can say, in the process of formation of a uni-negative ion from the neutral atom by addition of the electron, what is the energy evolved is called as electron gain. This is first electron gain enthalpy. We can say it is first electron gain enthalpy because the first electron is added. Now if we want to add electron to the ion which is formed, like we also spoke about this in ionization enthalpy. So this is one negative ion and we add one more electron to it, and now it will form X, 2 minus, of course also in the gaseous state. Now in this process we will say that delta H, which I said you can write like that, delta H will be equal to positive electron gain enthalpy. The second case, that is when the second electron is added, it is positive. This is a very important reason question asked. It's a reason question asked. The first electron gain enthalpy is negative, whereas the second electron gain enthalpy is positive. Why? What reason you will write? The first electron is added to neutral atom, so it will take the electron easily. In that process energy will be released. And the second electron is added to an anion. Uni-negative ion. So electron and anion both are negative, so there will be a repulsion between the two. Because of the repulsion, the second electron cannot be added that easily, so in this process energy will be required. You have application of this. You can apply this to this one, O in the gaseous state. If you add one electron, it will result in the formation of O minus. In this process electron gain enthalpy is negative. You need not remember the values. Okay, you should know what is exactly happening. this anion, again one electron is added. Now it will form O2 minus. Also in the gaseous state, now you write delta, that is change of electron gain enthalpy. You can write Eg this side also, it is fine. This is positive. So second electron gain enthalpy is positive. First one is exothermic, next one is endothermic. First one is exothermic, children. The second one is endothermic. Endothermic. Till here it is clear, right? Let us move ahead to the factors. Factors which affect electron gain enthalpy. Like we have discussed in the previous periodic properties, you have three major factors. I mean, these were already always there, right? First one is atomic size. If not atomic size, you can call this as atomic radius. Second, the effect of the nuclear charge. How will the nuclear charge affect? We will discuss this. Third is electronic configuration. Electronic configuration. Right, this was not there in atomic radius. Yes, in atomic radius, to some extent it was there. Why not? Because in oxygen, nitrogen we have compared. Yes or no? So this was there. So you have basic these factors which are affecting the electron gain enthalpy. Now let's see how. If the size of the atom is small and if you add electron to it, of course the nucleus and the valence shell, the distance is less, so it can take the electron easily. So if it can take electron easily means the energy released is more. And if you compare a larger size, the distance between the nucleus and the valence shell is more. When it is more means the nucleus cannot attract the valence electron, the added electron easily. Attraction will be less. If attraction is less, the less energy will be released. So we can say that atomic size is inversely proportional to electron gain enthalpy. Right? It is inversely. Bigger is this, lesser will be the electron gain enthalpy. Did you follow now? How small means if you are adding electron, the nucleus is closer to the valence shell. You can add the electron very easily, and if you can add easily means more energy will be released. Right? Next factor, nuclear charge. Again in the same you can understand. If the size is small, right, and you are adding, the shells are constant. You are going on adding electron to it. The nuclear charge also will be increasing with the addition of one electron. So if the nuclear charge is increasing, then the attraction for the electron is also more. So the electron gain enthalpy will be more. So what we can say, children, here is the effective nuclear charge is directly proportional to electron gain enthalpy. More the nuclear charge, more the effect of the nuclear charge, more will be the electron gain enthalpy, and vice versa. Lesser the this nuclear charge, lesser will be the electron gain enthalpy. Now let's see electronic configuration. How will the electronic configuration affect the electron gain enthalpy? If it is half filled, the configuration is half filled or full filled. Half filled or full filled configurations, then we have already discussed that they are very, very stable. They are very stable means they will not like to disturb their stability. They will not accept the electron readily. If they cannot accept the electron readily, obviously the energy released will be less. In a way, we can say these configurations, half filled and full filled, will have positive electron gain enthalpy. We will study this in the period. They will have positive electron gain enthalpy. Means which one? S2 completely filled, half filled P3, full filled P3, half filled d orbital, full filled d orbital, half filled f orbital, full filled f orbital. So these configurations, if they are present, they will have positive electron gain enthalpy or lesser. At times it is even lesser, not necessarily positive always. Got it? So now we will talk about variation of the electron gain enthalpy in the group and period. See the variation in the group. We will take this. We know down the group. What is happening to the atomic size? Atomic size is increasing. The effect of the nuclear charge down the group is decreasing. So what will happen to this electron gain enthalpy? Electron gain enthalpy down the group decreases. Atomic radius is increasing. When this is increasing, obviously the effect of the nuclear charge would be less, and so this also will be less. That means it is becoming less negative down the group. Right? If it is more negative, we say the electron gain enthalpy is high. Got it? But you will have some exceptional cases. We will talk about the exceptional cases separately. As of now, we are taking only in the group. Right? Now, let us see what about in the period. This is general aspect, children, we are taking. Yes? Across the period. Across the period means this way. What is happening to the atomic size is decreasing. Nuclear charge is increasing. So the electron gain enthalpy across the period, this is electron gain enthalpy across the period is increasing. I mean the ones which are present on the right hand side, it is more. Of course, there will be exception of the noble gas, half-fill, full-fill configurations, etc. We will be talking about those. Right? So let us take now what will be the exceptional cases, exceptions to this electron gain enthalpy. Let's see which particular group will have a different electron gain enthalpy. Group 2. Group 2. The configuration of group 2 is NS2. Completely filled configuration. You will find they will have low, and few elements have the positive electron gain enthalpy because they have completely filled configuration. They will not like to disturb their configuration. You have another one as group 15. Group 15 configuration is NS2 NP3, half filled configuration. If it is half filled configuration, again they are stable. So they are stable means it will be less. But for few elements we can say it is less, because they will not like to gain, but for few elements you will find the electron gain enthalpy is positive. Like you have example of nitrogen. Nitrogen electron gain enthalpy is plus 31. Right? Plus 31. So it is positive. Why it is positive? Because it is having half-filled configuration. For others, there are various other factors also acting, in the same particular group. You will find negative also in the same group, but they will be lesser negative. That means we can say that they have lower electron gain enthalpy. Let us also talk about group 18. Group 18. Children, group 18 configuration is NS2-NP6. NS2-NP6 means octet configuration, stable configuration. If it is octet configuration, then it is positive. You will find all noble gases have the positive electron gain enthalpy. These have the positive electron gain enthalpy. Right? Now let us see further. Group 16. Group 16, children, is NS2-NP4. You have the elements as oxygen, sulfur, selenium, tellurium, polonium. So what is our expected order down the group? The electron gain enthalpy should be decreasing. Electron gain enthalpy down the group should be decreasing. That is our expected order. But you will find, something different. Now what is the actual order here? See, let me write the order, then I will explain. Oxygen is lowest. Then you have polonium. After polonium you have tellurium. Then you have selenium, and then sulfur. So it is following the trend, but for this exceptional case goes down. You will place this below polonium. So polonium, below polonium is oxygen, means oxygen is having the lowest electron gain enthalpy. Now children, this is exception. You know that size is small, and till now what we have been doing is, if the size is small, then it should be gaining electron readily because it will have more nuclear charge. But this is the exceptional case where we see the configuration of oxygen is 2s2 2p4. 2s2 2p4 means the second shell is valence. Valence shell is second, in which the maximum capacity for the maximum electron that can be accommodated in the second shell is 8. of which 6 are already there. So the incoming electron will face more repulsion. The incoming electron will face more repulsion. We can say inter-electronic repulsion is there in oxygen. Okay, then what about sulfur and all? They have third, fourth, fifth shells where the number of the electrons can be more. Here capacity is only 8 but 6 are already present. Therefore the incoming electron will face more repulsion. Got it? Now let's see also 17. Children, group 17. Now group 17 is fluorine, chlorine, bromine, iodine, astatine. Right? What is our expected order? Down the group, atomic size increases, nuclear charge decreases. So we expect the electron gain enthalpy to decrease down the group. Right? We expect this to decrease. It is decreasing. This is decreasing, but for this fluorine. Again, this is a problematic thing. It comes here in between. Because you might think, why in the previous one we brought it down and here it is just here. Actually, there are many such factors. The nuclear charge also comes across the period. Nuclear charge is also increasing. So the incoming electron should be attracted also because this is smaller in size. Nuclear charge is more. But the other factor is also acting here, that is repulsion. In fluorine particularly, you have the inter-electronic repulsion overcomes even the nuclear charge. So what is the order here, children? Down the group we know it is decreasing. That means astatine is the lowest. Then you have iodine. Then you have bromine. After bromine is this one chlorine. After this is fluorine. This is fluorine, and you will have maximum as chlorine. This is very, very important. This is very, very important, children. Chlorine has the highest electron gain enthalpy in the periodic table also. Because we say across the period it is increasing, down the group it is decreasing. So it is present on the right, extreme right. Of course, noble gases we are not considering because noble gases are, having positive and octet also. So we expected fluorine to be maximum, but it becomes less. Chlorine becomes more. What reason you are going to write? You will write the configuration of both. This configuration is 2s2, 2p5, and chlorine configuration valence shell is 3s2, 3p5. So what are you going to write? In this, the valence shell is second. In the second shell, the maximum capacity is 8. Out of 8, 7 are already present. 7 are already present. Therefore, the incoming electron faces more repulsion. Very, very important question. This also affects the oxidizing property of fluorine and chlorine. We will talk about it later, right? Because there are many other factors which will be related to size and repulsion and all. What about chlorine? Chlorine has the third shell as the valence. Third shell valence, and the third shell can have maximum capacity of 18 electrons. Out of 18 electrons, only 7 are there. Only 7 are present. Therefore, the incoming electron will face less repulsion. So we can say from F to F minus, when the ion is being formed, less energy will be released. Whereas in chlorine, more energy is released. This is very important reason question asked. Is smaller in size than chlorine, the electron gain enthalpy of Cl is greater than fluorine. Got it? So I'll repeat the question. Question was, although F is smaller in size than Cl, Cl has more electron gain enthalpy. The reason is inter-electronic repulsion between the two. Got it? I hope you have followed this electron gain enthalpy concept. Next video we will be talking about the electronegativity and then the related properties to it. I hope you have followed. Thank you for watching.